Right. So in our example with the dog, right, if you were able to, get pictures of the dog competition obstacle course and perfectly recreate it in your backyard and just have your dog run those courses or run that one course, certainly it would get really good at that course. But again, that's not really showing generalization. It's not generally good at any and all courses that can possibly be created. And so the ArcAGI, the sort of, you can think of this as the training data, right? So this is not for the models. This is more for us humans to kind of look at and figure out if we can actually solve it, right? So you look at the example inputs and outputs and you see if you can spot a pattern. This might be fairly straightforward. The circuit may be a little bit different, but certainly still not super complex. Basically different colors here correspond to different sort of position of other colors around them, and in the case of this light blue one, nothing happens. And by the time you get to the last example, well, it gets a little tricky. And the goal here is to do something that's easy for humans. So if you have general intelligence, just like a human being, you should be able to figure this stuff out. But it should be very difficult for AI. So if all of us take this test and we get a certain percentage, and we'll call that like the human baseline, the human sort of level of ability on this test, then no currently available model, AI model, would be able to beat it. And so here they've set sort of that threshold at 85%. There were some people that sort of like pointed out that the actual sort of human baseline, human level is a little bit lower. 85%, we'll set that as like the level. If they get over that, then they will get the ARC prize. And so currently these are the high scores, the leaderboard for the sort of the public ARC AGI. And you can see those submissions, the competition notebook on Kaggle.com. Kaggle.com is, of course, this large AI and machine learning community, tons of data sets, lots of competitions. And of course, one of the competitions is the ARC AGI. So as you can see here, we're still quite a ways away from 85%. Which brings us back to that paper out of MIT, the surprising effectiveness of test time training for abstract reasoning. And so really fast. So we used to train models like GPT-4, for example. We would train it and then we would run inference. We would ask it questions. So there would be a period of training and then it would be ready to answer our questions. This model would be rather static and it would kind of spit out answers immediately. Next, we have the O1 model, and that was a little bit different because here is where OpenAI introduced us to this idea of test time compute, basically allowing the model to think through the answer and use more of the computational resources to think about the problem before answering. Which, by the way, that model, the Chinese model, DeepSeek, it seems to be they cracked the code on how to do that. As you can see here, it improves accuracy with test time compute scaling. So as you can see here, as the average number of thought tokens per problem, as it goes up, as we give it more time to think and talk its way through the answer, the accuracy keeps increasing. So they kind of like cracked that approach that OpenAI, they were the first ones to kind of introduce this to the world. Again, so that's the O1 model, the test time compute, and that's also the same thing that looks like this DeepSeek model is doing. But this new thing, it's something new entirely. It's called test time training. So just keep that in mind. Test time training, TTT, versus test time compute, TTC. This is kind of the OG model, if you will, the original, right? This one was the one that was referred to as Q star, aka Strawberry. And this is the Q star 2.0, if you will. That's not the official term, but it does seem appropriate. So they begin by stating the problem pretty well, I think. Language models have shown impressive performance on tasks within their training distribution, right? So if they got trained on that obstacle course, they know how to do that obstacle course. But they often struggle with novel problems requiring complex reasoning. Again, if it's a trick question, they haven't seen those types of trick questions before, they're going to fail at it, most likely. Novel, never before seen problems they struggle with. And so these people out of MIT, they investigate the effectiveness of test time training, updating model parameters temporarily during inference using a loss derived from input data. And interestingly, I think Mark Zuckerberg in the interview with Dwarkesh Patel did kind of hint at this a while back, saying that there's more of a blurring of a line between training and inference. So training is when we feed it the data, inference is when we ask it the questions, so input, output. But here you can almost say it's kind of getting trained while we're asking it to answer the questions. And so this idea, they're using this mechanism for improving the model's reasoning capabilities using the abstraction and reasoning corpus ARC. That's what it stands for. So the ARC AGI, and they're using that as a benchmark. And test time training significantly improves performance on ARC tasks, achieving up to a 6 times improvement in accuracy compared to base fine-tuned models. So they've used this TTT to a 8 billion parameter language model. So rather small, and they're achieving a 53% accuracy on ARC's public validation set. And by assembling our method with recent program generation approaches, they get the state-of-the-art public validation accuracy of 61.9%, which is matching the average human score. So again, the threshold for the ARC AGI is 85. There was a paper we looked at last time. We didn't read the whole thing, but they were saying, yeah, the sort of the average human score, it was somewhere in the 60s, I believe. I don't remember the exact number, but here they're saying so they've matched the average human score by using this sort of approach. And this test time training, it's important to understand that it operates in an extremely low data regime. Whereas the initial training might be massive amounts of data, this is very, very small amounts of data that it's getting kind of like continuously trained on. And so they're mentioning that the ARC corpus, right, abstraction reasoning corpus, is an ideal benchmark for testing limits of language models of their generalization ability, right? So the ability to kind of generalize to novel, never before seen tasks. And they note how current language models do perform poorly on the ARC currently. So how exactly is it doing all this magical stuff? Well, so test time training, TTT, this technique that we're talking about, enables parametric models to adapt during inference through dynamic parameter updates, an approach that remains relatively unexplored in the era of large language models. So it's adapting its sort of parameters, how the brain works, if you will, during the questions that it gets during inference. So as we're asking the questions from the test, it rapidly kind of trains itself up to be better able to answer that test question. So the model leverages the test data itself to improve its predictions. So the general TTT process works as follows. Starting with the initial model parameters, right? So basically it starts with its initial parameters like it was trained for, right? Static. For each test input or batch of inputs, so you can think of this as the test questions, like if you're answering a test, so it's any one of the questions, or batch of inputs where that's like the whole test or number of tests. We first generalize the training data from the test inputs. So that might be a little bit hard to grok, but the thing that really makes it clear for me, I actually gotta say thank you to Google